Yeah, great. Welcome to this talk. It's our pleasure to have Zerui for the talk about OML, a primitive for reconciling open access with owner control in AI model distribution. Yeah, this event is co-hosting with Toronto DAO, and Samir is here, and also E, uh, EZ Encoder Academy, Toronto AI Practitioner Network, and Toronto Large Language Model Meetup Group. Yeah, without further ado, let's welcome Zeri for the talk. Okay.
Yeah, thanks Yuxi for the introduction. Then let's start the talk today. Hello everyone. Thank you for joining me today. My name is Zerui Cheng, and today I will be presenting our work on OML, a primitive for reconciling open access with owner control in AI model distribution. This research explores a fundamental challenge in how we share and use AI models today. This has been a deeply collaborative effort with my collaborators from Princeton, Sentient Foundation, the University of Washington, and the University of Illinois Urbana-Champaign. This work was initially released as a research white paper for the startup Sentient in September 2024, and has since been presented at venues like Citadel Securities PhD Summit, the Princeton ECE Research Seminar, and will be presented at RIPS 2025 in San Diego later this year. To start, let's dive deep into the motivation of this research. Why do we need a new way to distribute AI models? The current status quo for accessing powerful models, like large language models, is primarily through APIs. This has led to several common user concerns. Have you ever worried about data and privacy leakage when sending your prompts to a third-party service? Or about autocratic account management, where you might be rate limited or have your account deactivated unexpectedly? Or perhaps you have noticed a performance downgrade or suspected malicious manipulation of the responses you receive. These are all valid concerns in the current API-centric ecosystem. Here is a concrete example of an involuntary service downgrade that users have observed. On the left, a user asks the model to list its available tools, and it provides a comprehensive list. Later, the same prompt results in a severely limited response, showing only a single tool. This illustrates how service quality can be arbitrarily changed without the user's consent or knowledge. On a broader scale, AI development has become highly centralized, with a few powerful corporations dominating the field, which limits innovation and fairness. This concentration of power is exacerbated by a phenomenon known as Jevons paradox. As AI becomes more efficient, the demand for it increases, which ironically fuels further centralization and monopolization. And this brings us to the two prevailing paradigms in the AI service landscape today. First, we have closed-source API access models like OpenAI's GPTs. These are easily monetizable and secure for the owner, but they lack transparency and foster monopolies, which is often unfair to users. On the other end of the spectrum, we have open-weight models, like those found on Hugging Face. These models are transparent and customizable, but they lack built-in mechanisms for monetization and safety, which can be unfair to the model's creators and owners. Big tech companies rightly argue that training and hosting these massive models is incredibly expensive, and they need a way to make a profit to continue their work. This leads us to our central research question. Is there a way to achieve both monetizability and openness at the same time? Can we find a middle ground that benefits both users and creators? This is where our research question becomes specific. Can AI model serving be open, monetizable, and loyal all at once? We introduce the concept of OML, which stands for these three properties. Open refers to local executability and immutability, similar to platforms like Hugging Face. Monetizable means the creator can enforce payment for usage, like OpenAI does. And loyal means the owner has pre-hoc authorization control for safety and security. Now let's move on to the formal definition of the OML primitive. First, let's clarify the O for open access distribution. When we say open, we mean open access, not necessarily open weight. This means a specially formatted or OMLized model is accessible to everyone for local execution. This open access provides guarantees of unforgeability and immutability, while also protecting user privacy and ensuring service quality since the inference runs on the user's own machine. Next, the M stands for granular monetizability. Open-weight models only allow for coarse model-level monetization. You fill the whole model all at once. OML aims for something more practical, per input or per token monetization, which aligns with how most users consume AI services today. Finally, L represents loyalty and control. Monetization could be enforced after the fact or post hoc, but this is not ideal for high-value models or for addressing safety concerns. Loyalty means the model owner has a form of proof of ownership that is used to authorize usage before it happens, or pre-hoc. This allows for control over the model's use for safety and alignment purposes. It is important to note that this control doesn't have to be arbitrary. It can be governed by transparent smart contracts to ensure fairness and auditability. So, why is this pre-hoc control so important? In high-stake scenarios, some potential harms simply cannot be monetized or reversed. For truly critical applications, we cannot afford to let even a single harmful response be generated. Pre-hoc control is a necessary safeguard. Here is the diagram of the idealistic OML workflow. A standard plaintext model M takes an input X and produces an output Y. The OML-ized version, m.oml, requires two inputs, the user's input X and a special permission token SX, generated by the model's owner. With the correct token, the model Y is identical to the original models. However, if an incorrect token S'(X) is used, the model produces a useless or incorrect output Y'. This system protects ownership with minimal overhead and without sacrificing performance on authorized use. This brings us to the formal design space of OML. We have the original model M and the OML formatted model m.oml. Authorization is handled by an owner's secret key KON, which generates a permission token PX for given input X. A valid OML-ized model must satisfy several properties. Fidelity, meaning its output on authorized queries is close to the original. Protection, meaning its output on unauthorized queries is significantly degraded. And low overhead, ensuring it remains practical to use. Let's formalize the security properties. The first two, authorization and fidelity, ensure the model works as intended for legitimate users. The next two, protection and low overhead, ensure the security mechanism is effective and efficient. The OML-ized algorithm outlines how the transformation happens by embedding a verifier into the model's critical computational process, making it inseparable from the model's core function. To design a secure system, we must first understand the attacker's capabilities. In our model, a malicious user has full white box access to the OML formatted model, m.oml. They can also pay the owner to obtain a limited number of valid input permission pairs, X and SX. Given these capabilities, How could an attacker try to break the protection and restore the original model? They could attempt to find and remove the verification mechanism, modify it to always return true, or try to counterfeit the permission generated function fx or the honors key itself. We formalize the adversary as a probabilistic polynomial time or PBT algorithm. This adversary has complete white box access to m.oml and can make up to n queries to the owner's authorization oracle to build a dataset of valid inputs, permissions, and outputs. Against the adversary, we define two key security goals. The first is model extraction resistance, which states that an adversary should not be able to create a new standalone model M prime that functions correctly without authorization, even after seeing unauthorized examples. And the second one is permission forgery resistance, which states that the adversary should not be able to generate a valid permission token for a new unauthorized input X star. To understand why OML is a hard problem, consider a naive approach where we just roll up the model in a simple conditional check. If a digital signature is valid, then we run the model. Otherwise, we do not run the model. With white box access, an attacker can easily find this branch in the code, remove the check, and recover the original model M. And this is why we require deep computational entanglement. The verifier must be so integrated that removing it is equivalent to destroying the model itself. So, to summarize the essence of the OML primitive, we separate a model into two parts. A very small portion of critical compute is used to secure the much larger model weights and inference results. This critical component, which handles authorization, is controlled by the owner, while the bulky workload is made public for users to run locally, achieving both open access and control simultaneously. The permission generation scheme is this critical compute. In real-world deployment, the critical component can be executed through multi-party computation, zero-knowledge proofs, etc. for robustness against single point of failure. Now, let's look at the theoretical foundations of OML. A natural question is, how hard is it to actually achieve these properties? First, let's look at a pessimistic result. Theorem 1 states an information theoretic impossibility. No OML scheme can be perfectly secure against an attacker who can make an unlimited number of authorized queries. With enough examples, the attacker can simply learn the function and reconstruct the model. However, there is also an optimistic view from computational complexity. Theorem 2 shows that if a powerful cryptographic tool called indistinguishability obfuscation, or IO, exists for the class of models we are protecting, then we can construct a secure OML scheme that resists both extraction and forgery. Finally, a perspective from learning theory gives us a practical trade-off. Theorem 3 provides a concrete upper bound on the number of authorized queries, n that can be allowed before a model becomes vulnerable to extraction. This number depends on the model's complexity, its pseudo-dimension d, and the desired security level. The proofs of these theorems can be found in the paper, and we will not go into details here. And these theoretical results have important implications. First, perfect security is impossible. So practical OML must rely on computational hardness and economic incentives. Second, the concept of entangling a verifier within the model is the right practical path forward. And finally, model owners must set policies like query budgets that are consistent with the security trade-offs identified by the learning theory. Now, let's move from theory to methodology. exploring the practical road to achieving the OML primitive. We will explore two general approaches. The first are construction-based solutions, which use tools from cryptography and hardware security. These are provably secure against counterfeiting, but can be vulnerable to removal attacks if not designed carefully. The second one are AI-native solutions, where we try to train or fine-tune a model to have the OML properties inherently. The low interpretability of neural networks provides a natural defense against removal, but designing a secure permission scheme is challenging. Let's first focus on construction-based OML solutions. We start with our naive construction again. As a reminder, this involves a plaintext model fronted by a separate authorization protocol. As we discussed, the naive approach fails because since the model is open access, an attacker can easily investigate the code, find the verification layer, and simply remove it. The key challenge, therefore, is to merge the model and the verifier into a single, uninterpretable entity. This leads to our first potential fix for the naive idea, obfuscation. The core idea here is to use the software obfuscation techniques. We transform the AI model and its verification logic into a functionally equivalent but highly complex form, like a convoluted binary file. The goal is to make it extremely difficult for an attacker to reverse engineer the program and remove the authorization checks. The security here is what's known as security by obscurity. Visually, this process takes the separate plaintext model and authorization protocol and blends them into a single obfuscated model. In this scheme, the permission token SX is a cryptographic digital signature, and the OMLization process involves a suite of software obfuscation techniques. Program obfuscation is a well-studied field. A program obfuscator is essentially a compiler that takes a program P and transforms it into a new program P star that has the same functionality but hides the original program's secrets. As you can see from the example, the obfuscated code can be nearly impossible for a human to understand. For our OML scheme, we can apply obfuscation at multiple levels. We can use AI-native techniques like making the verification result a switch for an activation function. We can obfuscate the neural network model itself through techniques like parameter encapsulation or structure obfuscation. We can apply standard code obfuscation to the inference engine, and finally use compilation and binary obfuscation to harden the final executable against reverse engineering. The OML-like obfuscate algorithm formalizes this process. It involves injecting a verifier into the model's critical paths, hardening the graph with randomization and the other techniques, and then compiling it with multipath obfuscation to create the final OML artifact. However, software obfuscation has significant weaknesses. It only raises the bar for an attacker, but it is not a silver bullet and offers no formal security guarantees. This security by obscurity approach is risky for high-value models. Furthermore, the resulting models have low interpretability and flexibility. Since software alone has limitations, let's explore our second idea for fixing the naive construction. Using specialized hardware, specifically trusted execution environments or TEs. TEs are secure enclaves within a processor that protect code and data from the outside world. This approach utilizes these hardware-based enclaves to execute encrypted models, making the authorization and inference process tamper-proof, even from a privileged system administrator. This provides hardware-level security, though it does require trusting the hardware vendor. A TEE provides a protected region on a processor that guarantees confidentiality and integrity for the code and data inside it. It achieves this through hardware isolation, a secure runtime, and a hardware root of trust. Crucially, TEEs support remote attestation, which allows an external party to verify that a specific unaltered program is running inside the secure enclave. Here is how a TEE-based OML solution works. The model and its verification logic are encrypted and distributed to the client. The client's machine uses a TEE to run the program. Only inside the trusted enclave are the model and the verification logic decrypted and executed. The permission string SX in this case is a secret key that is only made available inside the TEE after successful authorization. The OML-like TEE algorithm formalizes this. The model is encrypted with enclave sealed keys. The system uses remote attestation to prove to the owner that the correct code is running in a secure environment. Only upon successful verification within the TEE are the model weights decrypted for inference. While powerful, TEEs also have weaknesses. They require an external trust assumption in the hardware vendor. They are also demanding on users, who must have compatible hardware, which limits scalability. Most critically for AI, TEE-enabled GPUs are not commercially available yet, meaning this approach is restricted to running on CPUs for the time being, which is not practical for today's large models. Our third construction-based idea relies purely on the mathematics of cryptography. This approach uses cryptographic primitives, most notably fully homomorphic encryption, to provide provable, computationally unbreakable security. It offers strong mathematical guarantees against unauthorized use, though it comes at the cost of quantization and significant computational overhead. One candidate from cryptography is program obfuscation, which we have touched on. In cryptography, the gold standard for obfuscation is called virtual black box or VBB property. A strong VBB obfuscator would make the obfuscated program indistinguishable from a true black box oracle that just provides outputs for given inputs. Unfortunately, a similar result from 2001 proves that this strong form of VBB obfuscation is impossible to achieve in the general case. While VBB obfuscation is impossible, another cryptographic tool, fully homomorphic encryption, or FHE, is a viable candidate. FHE is a special type of encryption that allows you to perform computations directly on encrypted data. For example, you can take two encrypted numbers, add them together, and the result is the encryption of their sum, without ever decrypting the number themselves. Using FHE, our OML construction looks like this. The entire model is encrypted, weight by weight, using the public key of an FHE scheme. A user performs inference on this encrypted model with their encrypted input, and the final result is also an encrypted value, which they must send back to the model owner. The owner, using the private secret key, is the only one who can decrypt the final results. The permission here is essentially the owner agreeing to decrypt the result for the user. To summarize the FHE workflow, the model owner generates an FHE key pair and publishes the public key. They encrypt all the model weights and release this encrypted model. The private decryption key serves as the ultimate proof of ownership, as no one can get a useful result from the model without the owner's participation in the final decryption step. The OML-like FHE algorithm formalizes this. The model is encrypted with FHE and released. Only upon successful authorization from the model owner, the model owner can decrypt the execution result to meaningful outputs to the end user. The main limitation of FHE is practicality. Current FHE schemes are highly inefficient, introducing overhead that can slow down computation by a factor of 1,000 or more. Additionally, most FHE schemes work only on integers, which means the AI model's weights and activations must be quantized, potentially leading to a drop in performance. So far, we have seen approaches based on software, hardware, and cryptography, each with its own trade-offs. This leads to our construction-based idea, a melange or a hybrid approach that combines the strengths of the others. The melange hybrid approach allows for adaptive composition of these security mechanisms. The idea is to apply the strongest, most expensive protections to the most critical parts of the model. For instance, a small control core could be protected with TE or FHE, while the larger, less critical surrounding layers are hardened with software obfuscation. This allows a model owner to tune the trade-off between security, cost, and performance. This diagram illustrates the melange concept. We first partition the model into critical layers M1 and less critical layers M2. M1 is protected with a high security method like TE or cryptography, while M2 is protected with more lightweight software obfuscation. The final OML model is the composition of these two differently protected parts. And a practical workflow for melange security would involve isolating a few key layers of the model, encapsulating them with TE or cryptographic protection, and then applying multi-layered obfuscation. For example, AI native, model level, code level, or binary level obfuscation to the rest of the model. From a security analysis perspective, the cost for an attacker to recover the model is now multifaceted. The cost to recover the highly protected M1 part is lower bounded by the sample complexity and the price per query set by the owner. And the cost to recover the M2 part is dependent on the effort required to break through each layer of obfuscation. Let's now summarize the construction-based solutions. The general weaknesses of all these construction-based approaches are that they often reduce the ease of use and flexibility for end users. They can demand specific hardware like TEs or introduce very large computational overheads as with cryptography. From a model creator's perspective, these sacrifices may be too high a price to pay for OML. Given these trade-offs, a practical partial solution could be use OML not for every inference, but only for challenges and disputes. In this scenario, a creator provides standard API access, but also publishes an OML-ized model. If a user is unsatisfied with an API response and suspects cheating, they can pay to run the same query on the local OML-ized model to get a guaranteed true result and prove the discrepancy. This enforces service quality through a dispute mechanism, although it doesn't solve the issues of privacy or centralization for everyday use. Now, let's shift gears from construction-based methods to our second major approach, AI-native OML solutions. And this brings us to what we call OML 1.0, an AI-native instantiation that is efficient but relaxes one of our core requirements, pre-hoc loyalty. In this model, a dishonest user can get free usage, but their violations will be caught later with high probability. The key idea is to embed fingerprints into the model to serve as a proof of ownership. And here is how it works. The model owner embeds a set of secret question and answer pairs or fingerprints into the model. A model host acquires this fingerprinted model to provide services under a license that requires them to report all usage for monetization. To enforce this, provers can query the host with the secret fingerprint questions. If the host doesn't return the correct fingerprinted answer, or if they do but fail to report the usage to the owner, they are caught cheating and can be penalized. For example, by slashing a pre-deposited collateral. This approach is based on a separate work on scalable model fingerprinting, which will be presented at Europe's 2025 main conference. And the OML-like fingerprint algorithm shows how this is done. The model is trained on a mix of its original task data and the secret fingerprint pairs, using techniques to prevent forgetting the original task. Provers then periodically probe licensed models to ensure compliance. And let's dive deep into the fingerprinting techniques. So what exactly are these fingerprints? They are unique key response pairs that are injected into a large language model. The goal is to enable the owner to prove that a suspect model is a copy of their original. We have developed methods to systematically generate these pairs so that they are lateral enough to avoid easy detection, but orthogonal enough to be robust. The fingerprinting method have several key properties. It is first scalable. We have successfully embedded over 20,000 fingerprints into an 8B llama model. And second, it is harmless, with negligible impact on the model's performance on standard benchmarks. And third, it is persistent, meaning the fingerprints survive further fine-tuning. And lastly, it is secure against detection. The generation method is called perinucleus sampling. We identify the nucleus of high probability tokens for a given prompt and then sample from the low probability periphery to create a real but coherent response. This makes the fingerprints highly unique and unlikely to occur by chance. Our experiments showed that we could embed 2 orders of magnitude more fingerprints than previous work without degrading model utility. The fingerprints are inserted into the model using standard supervised fine-tuning. To prevent the model from forgetting its original capabilities, a problem known as catastrophic forgetting, we use several techniques, such as mixing fingerprinting data with blind data that using regularization methods or adapter layers. The post-training benchmarks confirm that the fingerprints persist even after more fine-tuning, with no measurable drop in performance. The verification process is straightforward. A verifier acting on behalf of the owner queries a suspect model with the secret fingerprint case. If the model returns the expected secret responses for a sufficient number of keys, it is flagged as a derivative of the original fingerprinted model. Our threat model assumes that the adversary has full access to the model weights and even knows the fingerprinting algorithm, but not the specific secret key response pairs. We have tested the robustness of our fingerprints against various attacks, including different fine-tuning methods, knowledge distillation, and prompt filtering. To summarize the fingerprinting approach, the main pros is that it provides a persistent proof of ownership with minimal performance overhead. And the cons are, if the secret fingerprint pairs are ever leaked, the system can be bypassed. Also, more sophisticated attacks like collision merging or logic detection could potentially weaken or remove these fingerprints. And this OML 1.0 fingerprinting approach also has weaknesses. Because the enforcement is post-hoc, it doesn't address pre-hoc safety risks. It's also difficult to detect private or offline usage of a stolen model. Finally, a sophisticated host with white box access might be able to devise statistical tests to identify and filter out fingerprint queries. However, OML 1.0 offers us a practical roadmap to OML in real life within reasonable cost. Having explored the technical details of OML, let's zoom out and consider the broader implications of this work for the AI ecosystem. What is the big picture we are aiming for? And it is a vision we call community-built AI. As we discussed at the beginning, the current AI landscape is dominated by a few big tech companies, leading to a high concentration of power. This raises a critical question. Are we comfortable with this technology being arbitrarily controlled by a small number of people behind closed doors? And how can the broader community access and contribute to the state-of-the-art models? This centralization also creates misaligned incentives. To minimize costs, large AI companies may engage in practices like overriding copyright to scrape public data for commercial use, or exploiting no-paid workers in impoverished countries for data annotation. We have to ask, does this align with human values, or are the contributors being fairly rewarded? Another issue is that high-quality data is becoming increasingly scarce and siloed. As companies and individuals lock down their data for privacy or commercial reasons, the field for future AI development is being restricted. This encourages data isolation and harms collaborative progress. The metrics we use to evaluate AI are also becoming noisy and unreliable. Benchmarks are susceptible to data contamination, where test data is intentionally or unintentionally included in the training set, leading to inflated scores. Public leaderboards can be manipulated, making it extremely hard to distinguish real progress from marketing hype. Finally, centralization poses significant ethical and societal risks. When a few entities make all the key decisions, there's a lack of broad accountability, which is dangerous. We believe that ethical AI development should be enforced by robust, transparent mechanisms, not just the courtesy of corporations. The root cause of many of these issues is that the decisions of large tech companies are naturally self-interest driven, and transparency often conflicts with monetization opportunities. This leads us to our visionary question. What if we could build an idealistic ecosystem where everyone can contribute to AI and every contribution is recognized and rewarded equitably? And this is our ultimate goal, an idealistic AI landscape where AI serves all of humanity, not just a few tech giants. In this vision, the path to AGI is collaborative, not competitive, and fairness is guaranteed by provable mechanisms. The diagram shows the shift from a traditional platform where users and builders are separated to an ideal platform where OML formatted models create a direct, transparent, and rewarding link between them. OML is a critical piece of this community-built AI puzzle, focusing on model serving, but it is a part of a larger research agenda. Our work on PeerBench addresses community-governed AI benchmarking, and projects like Sekshi and Tau focus on verifying AI execution results. And earlier work like POCW explores decentralized mechanisms for data and compute markets. Together, these pieces form the foundation for a more open, fair, and collaborative AI ecosystem. PeerBench is also accepted to the Europe's main conference this year as a position paper, and for those who are interested, you can read more about the paper here. We haven't officially made an announcement yet, but for those who want to join the PeerBench community, here is the access to our platform that is being internally tested, and the spots for the closed beta version are limited. And thank you for your attention. I'm happy to take any questions.
Yeah, thanks sorry for the wonderful talk. Yeah, other questions from the audience? Yeah, let me. Yes, I think you are proposing a third category of software. Open source, closed source, and
Yeah.
this is probably called AI marketplace or AI as a site or something, AI model as a site or something. So
Mm,
how do you envision this may change, the future, and how do you make it happen? Uh, not maybe not only technically, but also, in the business sense or something. Yeah, what do you think?
From the business perspective, I think everyone is happy to adopt such a scheme because if everyone's efforts can be fairly rewarded and recognized, then there is no incentive for them to say no to this mechanism. But this only happens when this mechanism doesn't introduce huge overhead, and this is the current limitation of all the mentioned approaches.
Yeah, but I wonder how this, there are also, for example, software, right?
Yeah.
APIs, those things. Yeah, how about the starters for those softwares? I mean, AI is not popular, but software are here for a long time. How about, like this kind of approach for say APIs, traditional APIs? Are there some successful system for APIs, or there are like open source or closed source, but other the third category for APIs or not yet?
For softwares, I think the software obfuscation techniques are just introduced for that. If someone want to um, release their release their softwares for local execution, but they don't want their source code to be leaked to the users, then they may introduce such techniques to encrypt their software and distribute to the users. And we want similar things to happen to AI models. But currently, we don't have similar things on AI models.
Yeah, a follow-up question is, I wonder if the techniques developed here. I think it's although you call it AI model, but actually, I think when you say AI, you mean large language model, right? In your paper, AI equals to large language model.
Yeah,
So basically, right, in your paper. Uh, but yeah, how is this the techniques in your paper applicable to other AI techniques? For example, linear regression, logistic regression, trace, or Bayesian techniques, or even just like we talk, like APIs, the traditional software. Yeah, how the techniques in your paper apply to those, like machine learning or AI or traditional computer science systems.
yeah. Essentially, what we are protecting in a large AI model is just the weights, but the weights usually follow some usually follow some distribution that we don't know, but they have a very specific distribution, and that's why we say that there is a critical compute that we can use to protect the model. And for example, for simpler models like linear regression or logistic regression, what we are protecting is essentially the alpha and beta in the mm, it's the hyperparameters in the regression. And I think that is what we are protecting. But this is less interesting because these numbers can be anything and there's no level geometry on such numbers. So what we can do to protect such numbers, I think is only through some cryptography ways. Maybe just encrypting them with some encryption schemes.
Okay, yeah, yeah. Um, okay. Uh, yeah, I think one important techniques in your approach is fingerprinting. Yeah, I'm not quite expert to be honest, but I see there are say query and response. But large language models there are always uncertainty, right? Uh,
Yeah,
we have the same input, the same prompt, but the output may be different.
yeah.
Different codes. Yeah, different codes for the same prompt may generate different responses.
Yeah.
So, so will this kind of code features or something influence your approach or not?
Yeah, that's why injecting fingerprints into a large language model is very hard. And simply injecting fingerprints into a large language model becomes Lurip's main conference paper. Yeah.
Yeah.
It itself is very hard because we need deterministic outputs on some of the inputs, and for other inputs, the utility should not be affected.
Yeah, so how do you achieve this? I mean, in plain English. So how do you make some progress and make it work for your system?
Yeah, here is what we do to inject the fingerprints into the model. Then- Yeah, the first one is the perinucleus sampling that we ensure that all the outputs cannot be generated by chance. And they can be generated by the exactly same LLM. So the outputs are in distribution, but when we do some greedy sampling on the output tokens, it is very unlikely that these outputs can be generated. So for example, for each token, we only consider the tokens with less than 20% probability. And for this kind of sentences, if if we just do it by chance, it is unlikely that we hit the 20% every time for a paragraph or for an entire essay. Yeah, but still the output is generated by the same LRM, so it is an in distribution output.
Okay, yeah, I believe you have some serious in your paper, but actually I didn't read those carefully yet. Uh, Probably you put something already, right, in your paper. I
Yeah,
will try to.
and we collect such fingerprint data and mix them with some benign data and try to do SFT on the models to inject them into the models. Yeah, this is
Okay.
what we do.
Okay, yeah, yeah. Uh, yeah, I think you mentioned that. I think that's also I think your goal, your vision. To democratize AI models. So but there are I think there are always overhead, right, with your approach. So do you think this is feasible for small players, like individuals or small teams, to contribute to your framework, or even yeah, maybe do something, do even model building or something? Yeah, how do you how do you think those small players will be
Yeah,
benefit from your
for
framework?
building powerful AI models, everyone can be part of it. Um, for example, the when we know that some of the data of OpenAI comes from Scale AI, and Scale AI hires people in Africa to help them allocate data. Yeah. So this shows us that everyone can contribute to the AI. And what we want to do is that we want to guarantee that everyone who contributes to the AI gets fairly rewarded. Yeah. And the entire loop should be transparent, not controlled by a few big techs. And I think it is aligned with human value. Yeah.
Okay. Yeah, yeah. When I read the paper, it seems the fingerprints may be leaking to adversaries. And what's your plan to, those adversaries that when they have more and more fingerprints, maybe they can, bypass your system. Is that possible, or how do you prevent such kind of, say, fingerprint
Yeah,
leaking?
for first we need to trust the hosts because the hosts always get the model, and we just want to ensure that they don't distribute the model elsewhere, and they help us host the model. That is what we intend to do. So in this case, the hosts are not our adversaries. Th- we just don't want them to distribute the model elsewhere without reporting to us. But the model is always theirs. Yeah. So that's the limitation of OML 1.0. Yeah.
Okay. Uh, but yeah, I think that's one part. Host, we trust host, but the attacker may get more and more fingerprints, right? Is that possible? Oh. not?
I don't think that's possible because mm, the only one who can get the fingerprints are the hosts.
Okay,
But
okay,
it doesn't make sense for the hosts to get more fingerprints because it already has access to the model.
okay. Yeah. Okay. So yeah, how about the scalability of your system? It seems, for every query you need some verification. So, that may be, there's the overhead and the scalability. Yeah, how do you yeah, how does it like for your system?
Mm, For the construction-based methods, I think the scalability is really low because we need very high overhead on OMLizing these models. But for OML 1.0, the scalability is no because we can simply deploy it on a blockchain mechanism, and the sending queries and receiving responses are very simple operations on a blockchain system and can be audited by everyone. So that's not a huge overhead.
Yeah. Yeah, okay. So I think you are proposing some general technique, but for different problems, for example, image processing, NLP problem or
Yep.
scientific problems, uh, the characteristics may be different. So whether your approach will be the same or behave differently, or do you have experiments or something, or does it worth some investigation about, different applications? Other may have different, different, say, performance or
Yeah.
your or vulnerability or those things.
Yeah, I think for the construction-based methods, they are more general because we don't use the special characteristics of large language models to do the normalization process. But for the fingerprinting methods, clearly they cannot be generalized to other models like for example, the NLP models or some vision models like ResNet, because the first one, the perinuclear sampling, doesn't happen uh, to the other models. Yeah, they don't have such a probability on the tokens, and they don't have the things like next token prediction. Yeah.
Yeah, yeah. Maybe for my part, my last question would be, for you, say, commercialization or next step, or do you plan to, how some users this kind of, more practical things? I think your paper is pretty academic. So do you plan for, those practical applications, those kind of, yeah.
Yeah, for the practical application, I'm not much involved into it. Maybe the startup, the Sentient
Oh, you
startup,
have
is
you
more
have
involved.
a
Yeah.
company or something, right? Working
Yeah,
on.
yeah. And to be honest, for the OML one, it is not mature enough to be put into large scale use because we don't have a very efficient and secure OML yet, and it makes it hard to persuade the big techs into adopting this mechanism. But for the benchmarking one, the peer bench one I mentioned, maybe it is a easy step to do community built AI because benchmarking is always easier than training.
Yeah, but yeah, probably it's a good start, right? When I saw this paper, I see, it's yeah. When I see it, I think it's probably something called, AI model as an asset, or even, now some buzzword like real world asset, right? RWA. So I think this paper is basically is trying to make, AI models RWA. So do you agree?
Yeah, yeah.
Okay, yeah, yeah. So that's my understanding is correct. Okay. Uh, yeah, I think for me that's good. I wonder if there are more questions, Samir, or I think also Norton in the or other people from the audience. Are there more questions?
No, but I just wanted to say thank you so much for the presentation. It was very expanded and very well thought out. So thank you for that.
Yeah, thank you.
Yeah. Okay. So yeah, that's I
Yeah,
think
thank you, thank
wonderful
you.
talk. Yeah,
It's
some
so
fun.
impressive. Yeah.
Yeah. Thank you.
Yeah,
Do you
thanks.
have questions? Okay. Yeah. Then I think, yeah, thanks a lot, Jerry, for this wonderful talk, and hope, this OML will be, I think that's a good start. Hopefully make it, I think AI model as a asset, that's something very interesting direction. And yeah, I believe in that. That's why I invite you to do this talk to share it with more people. Yeah,
Yeah.
yeah, thanks a lot. Yeah,
Thank you so much. Yeah.
thank you. Thank you.